Discuss about the application of refraction. But before moving further, for the application of refraction, we will discussed about total internal reflection. Then we will discuss about its application. So right now it is called as a total internal reflection. Now, total internal reflection is something new for you. Very first thing we will learn about over here is that what is actually total internal reflection is. So first of all, let's assume that we have a such type of a very small container or any large container. In front of you, I am putting a small container and there is a source inside this water or maybe some media. Right now, I am putting that this is N1 media and this is called as a N2 media, and I am putting that N2 is greater than N1 media. The second medium is larger than the first medium. Our second medium જે છે એનો refractive index is higher than the first medium. And a source is where? Source ક્યાં છે? તો source જે છે આપણો, it is inside that container. So what happened then? So gradually I'm putting right now some normals and then we will discuss that how it is bent. So let's say I'm putting that some of the normals. These are the normal lines. And gradually one moment will arrive that my ray will be coming back into the same media. So now I'm putting some of the rays. What happened then? Let's see. Very first thing that I'm putting my ray over here is that it is holding two type of thing. Very first thing that continuously I'm applying ray onto the normals. And then gradually you can see that what happened next. Every time you are aware that whenever my ray is coming out from the thicker media and then it is now back into the thinner media, you can see that what happened actually. Whenever my ray is coming out from the thicker media to the thinner media, you are saying that my ray actually is deviating its path, and its deviation will be what? It is getting away from the normal. And then what happened? It is getting away from the normal is that it is somehow, first of all, it is past, now getting more away, then getting more away, getting more away. And one moment will arrive that my ray will become parallel to the surface. And after that, what happened? After that, all ray will be coming back into the same media. So actually, I didn't want that. Maybe my ray will come back into the same media. But one moment will arrive that my ray is gradually getting away from the normal, getting away from the normal surface. And then one moment will arrive, it is becoming parallel to the surface. And whenever it is becoming parallel to the surface, then my ray, after interval of a time, is coming back to the same media. This is how it is behaving as a total internal reflection. So you can say that you can put first of all some definition for that one. It is called as a when ray is coming out from one medium and one moment will arrive when this ray is becoming parallel to the surface. And after that, all these rays coming back to the medium or back to the source medium. So this is how it has been placed as. So now this is how you
सर
can put that.
रिफ्लेक्टेड रे पैरेलल है.
What do you
पैरेलल कौन सी रे है सर?
पैरेलल
पैरेलल रे
अगर आपको देखना है तो पैरेलल वाला ये वाला है, ये ब्लैक कलर का. लेट्स से आई एम पुटिंग वन एरो ओवर हियर तो इट विल बी क्वाइट क्लियर टू यू. तो ये वाला है, देखिए ये वाला जो है वो सरफेस से पैरेलल बना हुआ है ब्लैक कलर का। चलिए
हाँ,
ऐसे शो कर देते हैं, इट इज इन अ मरून कलर, तो इट इज बिकमिंग पैरेलल टू द सरफेस जो दोनों को सेपरेट करती है, एंड आफ्टर दैट ऑल दोज रेज इज कमिंग बैक इनटू द सेम मीडियम, so that is how it is called as a total internal reflection. Yes, we were discuss about that. My ray is coming back to the same media, and that is how it is called as a total, or you can say reflective surfaces. That is called as a total internal reflection. Now, in a total internal reflection, I want to apply that my Snell's law. What will be the condition for the Snell's law? So first of all, I'm putting that Snell equation n1 sine theta 1 is equals to n2 sine theta 2. Chaliye, remembering that our previous figure, let's say I have drawn such type of structure and my ray is coming from the second media to the first media. You can say okay, it is starting its journey from second media and it is ending its journey from this media. So angle of incidence is called as the angle of reflection. Now N1 is the condition where you can say that refractive index for the air. It is called as a 1. And now one more thing you can have after this condition, this is normal. Your ray is becoming parallel to the surface. And then after that, all those angles, all those rays which are coming back to the same media, it is holding that critical angle. So first of all, I am putting that 1, and here initial angle is becoming 90 degree, that is why it is called as a sine 90. N2 is called as a refractive index of another media. I don't know what is the value of it, so I'm putting that N2 equals to 1. And sine theta 2 is that I'm putting that as C. So in addition, you can say that what is a C? It is called as a critical angle. Critical angle is what? After this angle, all my rays coming back to the source media. This is how it is called as. So this is how N1 is called as a 1, sine theta 1 is called as the initial angle, which is making an angle which is called as a 90 degree. And then sine theta 2, that is called as my this angle. After this angle, all my rays are coming back to the all my rays are coming back to the original source. So
के अंदर मीडिया में आ रही थी।
हाँ, तो उसके बाद जो भी rays होंगे, it is coming back to the original medium. So that is why N1 is 1 because it is air. It is actually known. Sine 90 is called as a 1. N is called as a refractive index of another media. See, I am not talking about that N2 is called as a water or glass or something. It is applicable to all those medias which are available to us and which are holding the source. Instead of this N2 media, I will place that glass है, तो भी क्या हो सकता है? The total internal reflection may happen. So now we will see its application as well, and we will apply that. It is also applicable to the optical fiber. We are just after this theory, we are supposed to learn it. And another thing is called as the diamonds are look like a shiny. This is only because of the total internal reflection. तो चलिए फोकस बना देते हैं अपने इक्वेशन को। तो हमारा इक्वेशन हो गया कि भाई sin c is equals to तो 1 upon n, और you want to find it out this critical angle, so c is equals to sine inverse 1 upon n. These are the equations for the total internal reflection, which is somehow different from our normal reflection. Normal reflection में क्या होता था कि भी our incident angle and reflection angle both are in the same media. यहाँ पर कंडीशन क्या है? इंटरनल रिफ्लेक्शन में एक तो रिफ्रैक्शन होना चाहिए इन अ स्मॉल अमाउंट. सेकंड थिंग इज दैट इफ अनदर मीडिया इज अवेलेबल देन इट इज पॉसिबल. एक मीडिया है तो नहीं होगा. एंड थर्ड थिंग इज दैट अवर रेज कमिंग बैक इन द सेम मीडियम. तो N2 में से सम वेव रेज आर कमिंग आउट फ्रॉम द सेकंड टू द फर्स्ट मीडियम. Another thing is that some of the rays coming back into the same medium. तो रिफ्रैक्शन का भी प्रॉपर्टी दिख रहा है and reflection का property is also observed. So it is a combination of a two type of phenomenon. So it is only possible whenever you have a two or more than two surfaces are available, then and then this total internal reflection may happen. Now, in a total internal reflection, I have just told you that it is following one more thing, one more phenomenon, and one more application. So, first of all, I will discuss about phenomenon. The very first phenomenon is called as a mirage. It is basically called as a delusion. Normally, what happens then whenever you are moving on a highway, it is look like something scattery, something, some liquid is floating on the surface. So what happened then? Our road is holding nothing. It is a purely behaving as a reflective surface. And around that, that is a media of air. So I'm putting that N1 is called as a 1 and that is called as air. Gradually temperature is higher. Whenever your road is gradually getting higher, getting heated, its temperature is hot. So the ray, the temperature, which is at the surface of the road and the temperature in between the road and above surface, both are different. You can say that I am putting some slots over here. So let's say this amount of a slot and another slot is over here. It is not visible, but for our understanding, I'm putting such type of slots. So you can see entirely above the road, these are the such type of slots. Let's say slot number 1, slot number 2, slot number 3. In a slot number 1, the air which is passing in contact with the road or surface gradually gets heated and its temperature is lower. So temperature is higher. Is temperature is higher, that is why its refractive index is lower. Because temperature or reflective index का relationship है जो है, it is in the inverse proportion. So you can just imagine that inverse proportion में temperature high होगा, denominator high, तो n is lesser than 1. तो एक तो ये हुआ, the air which is in contact with the road, तो gradually refractive index will be lower 1. ऊपर जाएंगे तो gradually temperature down होगा तो refractive index will gradually increase. So I'm assuming that जो contact में हवा आई थी on the road, it is having refractive index 0.5. The air in a slot number 2 is gradually get thicker. It's having refractive index is 0.7. And above than that, temperature is somehow lower compared to the slot number 1 and 2. So my refractive index is 0.9. And above all, my refractive index contains the air containing refractive index that is called as a 1. So you can see that all those different slots available to me. Even though you are in the same media, बोलेंगे सर मैं तो air के medium में था, but yes, you are having higher temperatures at a different points, so you can see that your refractive index is different at different slots. So the person who is viewing from another end will see that some illusions. So actually he will see that whenever there is a tree or some vehicle over there, its image is somehow scattered on the surface of the road, or maybe liquid is floating on the surface of the road. So such type of thing which is only possible because of the mirage, it is a total internal reflection. The rays which is passing from your eyes is gradually inside scattered frequent interval of a time, frequent amount of time. So frequent interval of time is happening over here. So what happens? It is look like something, some imaginary images will be there. So this is the conclusion of total internal reflection. It is a natural process happens. Another thing which is the device actually our human being has developed, it is called as our optical fiber. This is the instrument which has been used in so many applications. Very first thing, it is used in medical operations. Sometime to do some of the internal organs of a human body is study. We are using optical fiber. It is called as endoscopy. And another thing, it is used in the terms of a communication. So first of all, in medical history, it is also used. So that is called as endoscopy. Hope you are aware about the word endoscopy. It is called as internal study of or systematic study of internal organs of human body. It is endoscopy. And another thing, it is right now very much popular. It is called as a communication. Right now, we are on the verge of getting one more type of revolution in internet history. It is called as a 5G technology. So 5G technology is only because possible because of the optical fiber. gradually you will say that each and every corner of the country is gradually getting such type of connections. So what type of connection? So you can say 5G is possible because of optical fiber. Yes. The optical fiber is working on a which principle? So the optical fiber is working on the principle of a total internal reflection. Let's see how. In the past, they've asked the theory of optical fiber, but right now in this gradually new syllabus, they have removed it, but you have to understand this phenomenon. Optical fiber, first of all, made up of what? Optical fiber is made up of a fused quartz, glass, and PVC as well. So first of all, it is made up of a quartz and glass, sometimes PVC and plastic. But optical fiber made up of a PVC, it is of a poor quality. But quartz and glass, it is of a good quality. So optical fiber, first of all, made up of a quartz and glass. Now I'm applying a ray of light onto its surface. Then what happened? Let's see. On one surface of the optical fiber, I am putting that my ray and I am drawing one normal over here. So let's say this is my normal. Gradually, my ray entering into the optical fiber, you are aware that whenever my ray is coming out from the air, or you can say a thinner medium to the thicker medium, it is getting near to the normal. So my ray is gradually coming near to the normal and somehow deviated from these surfaces. So at internal period of time, it is attaining total internal reflection. And then one moment will arrive, my ray will come out. And you are aware that whenever it is coming out from the some thicker to the thinner media, it is getting away from the normal. I am drawing a normal over here. So now it is getting away from the normal. So now I am putting that such type of arrow. So this is how my total internal reflection will behave. Now one more thing I want to mention over here is what? First of all, optical fiber contains two different parts. Internal part is called as a core and outer part is called as a cladding. So internal surface of the optical fiber is called as a core and outer these surfaces and these surfaces are called as a cladding. Let's say cladding, I am putting that refractive index is 1 and for the core part I am putting refractive index is 2. So its a condition is that N2 is greater than N1, or you can say that N refractive index of a core is greater than N of a cladding. So this is how it is behaving as. The core and cladding parts are there. So now what happened then? I have placed my ray which is gradually entering into the optical fiber, and you are aware that its internal reflection or refractive index is more compared to the outer surface. So it is gradually facing that total. Yes. So it is behaving as a total internal reflection. Now, if it is behaving as a total internal reflection surface or total internal reflective surfaces, then what you will observe and how it is possible. Very first thing is that if you are passing that voltages from the optical fiber, you can pass that electromagnetic waves. It is called as the EB waves or you can say EM waves. It is also in the terms of optical signal. How it is possible? Let's see. Okay, let's say I want to first of all transfer my voltage from one location to the another location with the help of optical fiber. So what I am doing over here is that first of all, before this one end, left hand side end, I am putting one device. It is called as an optoelectronic device. This function of optoelectronic device is that to convert this voltage into the signal. So it will convert your voltage and the signal or voltage or current into the terms of a signal. Signal means waves or a ray. Then it is gradually passing frequent interval of a time. It is facing total internal reflection and onto the another end. Onto the another end, there is another device which is called as our converter, or you can say that it is converting your voltage signal, or you can say that your signal to the voltage. It is called as our one type of sensor. तो मीनिंग ये हुआ कि वोल्टेज ट्रांसफर करना है तो वोल्टेज को ऑप्टो इलेक्ट्रॉनिक डिवाइसेस से अपने सिग्नल में या तो रे में कन्वर्ट कर दीजिए, ऑन अनदर एंड आपका जो रे है उसको फिर से वोल्टेज में कन्वर्ट कर दीजिए, सो इजीली ट्रांसफर हो गया। तो आपको पता है कि भी हमारा नॉर्मल कंडक्टर होगा, इट इज कंटेनिंग रेजिस्टेंस, यहाँ पर कोई रेजिस्टेंस का चांस ही नहीं है क्योंकि वी हैवंट यूज कंडक्टर एज वेल, it is a purely insulator. You are aware about that quartz is a purely insulator. So purely insulator है, even though you can get around 99.9999% transfer rate. तो हमारा ट्रांसमिशन जो रेशियो होगा वो काफी रैपिड होगा compared to the velocity of electron. It is too much rapid, so it is used in the terminology of voltage transmission. दूसरा, I have used this word, that is it is used to study that internal organs of human body, that is called as our endoscopy. So for the endoscopy, what we will do? For the endoscopy, we are again putting one end of optical fiber into the human body, and on the another end we are putting a camera. And the size of your optical fiber is 0.05 millimeter. It is even smaller compared to your human hair. So this is how optical fiber will be having such type of a thickness. So optical fiber is a such type of thing. One more thing I want to mention over here is that I have one pen in my hand and I am putting 5 to 6 pens or putting such type of a bunch. Let's say it is not holding this much type of diameter. This is the only thickness. This thickness of a optical fiber is providing internet to the entire Asian continent. So you can imagine that how much powerful this optical fiber would be. Someone says, here I have a habit to chew the chewing. Yes, if you have the habit to chew the chewing, your optical fiber is softer than that one. If I'm putting and giving you a small piece of optical fiber to give you, you are supposed to chew it, you can say that optical fiber is very much softer compared to your normal chewing gum. So this is how the application of, or you can say that beauty of optical fiber is. One more thing is that optical fiber, you are bending your optical fiber interval of a time so many times, number of turns will be there, but it is not at all harming. It is not damaging your signal. Even though you are bending it, your signal will come out automatically. So these are the applications of, or you can say advantages of total internal reflection, which has been used in optical fiber. So this is the instrument. Yes, in a communication chapter as well, we also learn about the optical fibers applications. So we will discuss about that in a later part. Last not least part, it is called as our thing, which is called as our diamonds. Diamonds look like a shining. Actually, diamonds don't shine. तो फ्यूचर में जो भी लड़कियां हैं वो अपने नियर डियर से डायमंड लेने वाली हो तो उनको बोलना चमकने वाला डायमंड नहीं चाहिए। तो चमकने वाला डायमंड दिया है तो उसका मीनिंग ये हो रहा है कि इट इज अ प्योरली अमेरिकन डायमंड विच इज नॉट एक्चुअल डायमंड। तो डायमंड अपने आप नहीं चमकता है, इट इज ओनली बिकॉज ऑफ द टोटल इंटरनल रिफ्लेक्शन। इट मीन्स मैंने यहाँ पर कोई रे दे दिया है तो माई रे इज ग्रेजुअली डेविएटेड फ्रॉम द एक्चुअल पाथ एंड इट इज डेविएटेड, and that is how it is total internal reflection may happen. Number of times my ray will collide onto the surface of the diamond and it is how look like a shining. Number of times, I'm using this word frequently at every surface, it is gradually, I have shown very less number of rays which are colliding on the surface, but a tremendous number will be there. So it is colliding with the surface number of times. And because of this collision, my ray will come out after that at a later part. And that is how the person who is viewing it from the outside will feel that diamond is shining, but actually diamond is not shining. Whichever diamond you are viewing in the advertisement industry, you can see that in television as well. They are putting purely a gimmick. They are putting a small source of light at the back side or from the bottom side, and that is from the up view or side view. You can see that diamonds are shining. So whenever you are purchasing a proper or actual diamond, it is having matte surfaces. It does not look like that much shinier. And whichever diamond which are been shown into the advertisement industry, it is purely made up of a glass, nothing else, or polished. So total internal reflection is the phenomenon which has been followed by the diamonds, and that is why diamonds look like a shining. It does not contain their own shining. So this is the context which we have discussed